Hi, everyone. Thank you for joining today's talks in large-scale TTA as part of USACM, and really appreciate, and I'm very excited that we have Professor Julian Norato for today's talks. And Professor Norato is an associate professor in University of Connecticut. And his expertise is in the computational mechanics. He got his master and PhD in mechanical engineering from University of Illinois at Urbana-Champaign. And then after his PhD, he worked for a long time in industry, especially in the Caterpillar. He was the leading person for code development in the Caterpillar. And after his journey in the industry, he joined University of Connecticut. And his work is very close actually to common area between the academia and industry. As I was talking with him in the side chat, if you heard that he is one of the people in the optimization community that really making good connection for the academia and industry, specifically creating tools that you can implement directly to the industry. And always I have enjoyed his talks, how he's using his methods to implement some of those in real industrial application. In his work, he achieved many awards, including NSF Career Award in 2018, in 2017, Office of Novel Research Young Investigator, 2019, ASME Design Automation Young Investigator. Even in the industry, he got an award in the Caterpillar called Caterpillar's Move to the Mountain Award. So you can look at his bio in his page in Connecticut. With this, I give room to you, Julian, and we are waiting to listen to your talk. And you can share your screen. So,
first of all, thanks very much, everyone, for making time today to come to this talk. Today, I'd like to talk about some of the techniques that we have been developing in our group for the last years on topology optimization with geometric primitives, and particularly because this talk is for the large-scale TTA at USACM. The focus is going to be on a subset of our work that applies to large-scale design problems. So first and foremost, I always have to thank my students. As you know, they are the ones who really do the bulk of the work. So really all the things that are going to that I'm going to show today and that you're going to see are really coming from their work. And also I'd like to acknowledge the agencies and companies that have been sponsoring the work in our group. So I hope most of you, if not all of you, are familiar with topology optimization, or at least have heard of it. But if you haven't, I'd like to just briefly say that topology optimization is a set of techniques to optimally distribute material within some prescribed design region. And optimally means in terms of some optimization problem in which we're minimizing some function of interest subject to some constraint. Typically, the goal of topology optimization is to achieve lightweight design. And so one of those functions is typically a function that quantifies the amount of material that we have. And the other function is typically a function of structural performance that requires, to be able to evaluate that function, requires the solution of a partial differential equation, typically through the finite element method. Now, prevalent techniques in topology optimization, which are the ones that are most represented both in the literature as well as in commercial software, use what I would call a field representation, right? And so the most popular techniques are the density-based method, in which you have, for instance, element-wise densities, right, that dictate whether you have material or not in the design, and the level set method, in which the boundaries of the structure are given by the zero level set of some function, and the values of that function are typically associated with nodal values in the finite element mesh. So in both cases, we have a field representation, right, which is discretized using the finite element mesh. That is the way in which we represent the design is tied to the finite element mesh that we use for the solution of the partial differential equation. Okay. Now, geometry projection, which is the set of techniques that I'm going to talk about today, is different than these field representations in that the structure is described by a combination of geometric primitives, typically simple geometric primitives like this bar. And unlike density-based and level set methods in which the design variables are, for example, the element densities in the case of density-based methods, or the nodal values of a level set function in the case of level set methods, in geometry projection, the design parameters are geometric parameters that are directly associated with the dimensions, the position, and the orientation of these primitives. For instance, for this bar, the design variables could be the positions in space of the endpoints of the axis of the bar and the width of the bar. And the idea of the geometry projection is to have a differentiable map between these geometric parameters and a field representation like the density representation. And the reason we want to create that map, right, is that we want to retain the significant advantage that field representations have, that any time that the design changes, you don't have to remesh, right? You don't have to recreate the mesh, and that's a huge advantage, right? And we want this mapping to be differentiable because we want to be able to use efficient gradient-based methods for the optimization. Those are the ones that we use for the most in structural optimization because they are the most efficient. They are the ones that require the fewest number of function evaluations. The original motivation of these geometry projection techniques, and actually going back to what Ahmad was saying about my industry experience, was to try to design structures made of assemblies of geometric primitives. However, as I'll show today, over time we realized that this representation of the structure actually opens up quite a bit of other opportunities to solve problems that cannot easily be solved with the field representations. So how does the geometry projection work? We have the parametric representation that I mentioned. So for instance, the design variables here would be the positions of the endpoints of the axis and the radius of this bar. We also have this membership variable that I'm going to talk a little bit more about in a minute, but essentially this membership variable, if it is 0, it means that we're removing the bar entirely, and if it's 1, then the optimizer is telling us that we need to keep the bar. And so to obtain what we call a projected density for one of these primitives, the first thing that we do is to compute the sign distance from a point to the boundary of the primitive. And for certain geometric representations, so this is what we call an offset solid because all the points on the surface of this solid are equidistant from this medial axis. For these kinds of representations, it's very easy and very fast to compute the sign distance. And actually, we have closed form expressions for the sign distance as a function of the geometric parameters. Once we have that sign distance, we essentially pass it through what is a Heaviside or a smooth or regularized Heaviside function, if you will, to give us our density. So for instance, if we have a point X out here such that some window around that point does not intersect the primitive, then the density that you get is 0. If you have a point that is inside the primitive, right, and a window that contains that point is entirely contained inside the bar, then essentially the sign distance is larger in magnitude than the radius of that window. And so then we're going to end up with a density of 1. And finally, if we have a point whose sign distance is in magnitude smaller than the radius of the sampling window, then we get an intermediate value of the density, right? So the important thing here is we have this mapping that takes us from the geometric parameters that describe the primitive to a sign distance field to this projected density. If I change the values of these parameters, for example, if I change the position of one of these endpoints, right, I just do the mapping again, and then I get a new set of densities. And again, I don't have to recreate the mesh, right? That is the advantage. Not only that, right, but the fact that we have density representation of this primitive means, just like in density-based methods, that this primitive can be completely disconnected from the rest of the structure, and that is fine because the void region has some small, negligible but non-zero stiffness, right? And so the optimization has the capability of having these primitives sort of float until they end up connected to other parts of the structure during the optimization. Now, the membership variable that I was talking about multiplies the projected density that I just described, and then we raise it to a power p. So this is very much like the sim penalization in density-based methods, right? And it has exactly the same effect. It penalizes intermediate values of that membership variable. And that is because, as you'll see in a minute, we use these effective density to define the material properties so that regions of the structure or regions of the design space that have an intermediate value of this density are poor in terms of stiffness to weight ratio. Then the optimization will push these primitives, it'll push these membership variables to be either 0 or 1, right? That's what the penalization does. And this is very, very advantageous because it means that regardless of the dimensions, position, and orientation of a primitive, the optimizer can remove that primitive simply by making the membership variable 0. This is not possible in the other major technique for feature mapping topology optimization, which is the method of moving morphable components. The MMC does not have this feature. So in MMC, to be able to remove a primitive, it's necessary that that primitive either quote unquote hides behind another primitive or that it becomes so small that it has no effect on the analysis. What I just described is for a single primitive. So when we have multiple primitives, we can have two situations. One situation is when all the primitives are made of the same isotropic material. And when that is the case, we can combine all of the primitives using a modified p-norm, right? So we take the effective densities for all of the bars or all of the primitives. And the p-norm, as you may recall, is an approximation of the maximum function. So wherever they intersect, you're essentially getting the maximum of all the effective densities of all the bars at that point, right? Which is essentially a Boolean union, right, of solids. In parts of the design region where there is no primitive, where essentially a point in the design region that does not intersect any of the primitives will have an effective density of 0 for all of the primitives. So this whole term is 0. You get rho min to the p. If you take the p root, then you just get rho min. And so in that way, essentially, you have a low stiffness material in the void region. We also have a different combination of primitives that is more versatile, and this one uses the softmax function, which is actually widely used in machine learning, right? And the softmax function is just another differentiable approximation of the maximum function, but it has the advantage that it expresses the maximum of a set of values as the sum of some weights for each one of the values times the corresponding value. With the characteristic that from the equation of these weights, then what you'll find is that the component that has the maximum value will have a weight of 1, and all of the other components will have a weight of 0. And this is what's called a one-hot vector, right? And so with this approximation, or with these weights more specifically, we can define the tensor of effective material properties in this way, where we're actually adding for all of the components the weight coming from the softmax times the effective density times the elasticity tensor for that bar. This is a lot more versatile than the previous interpolation, because in this one, we can have a different elasticity tensor for each bar, meaning they can be made of different materials. Or they can be made from the same material, but if the material is anisotropic, then the values of the components, obviously, they necessitate the rotation of the properties or of the primitive in a space. For instance, if you have fiber reinforced bars, right? And so even if it's the same material, the actual numeric values of the components of the elasticity tensor are going to change every time the orientation of the primitives changes. The geometry projection is what we called in this review paper a map then combine approach, in which essentially first you do the mapping for each one of these primitives, meaning first you obtain a density field for each one of these primitives, and then you combine the density fields, right? The opposite approach, which we call combine and map, which is the approach adopted by the MMC method, is that first all of the primitives are combined into a single geometric representation, and then they are mapped onto the mesh for analysis. Now, in principle, they may look like at the end of the day would be the same, but the difference comes from the membership variable that I was talking about. So in this example here, we have three primitives, and then we start modifying the membership variable for that diagonal bar from 1 to 0.8 to 0.6 to 0.1 to 0. And you see that what we're achieving here is that without having to change the dimensions or the position or the orientation of this diagonal bar, we can remove the bar entirely from the design simply by making the membership variable 0. And this is really very convenient in terms of improving convergence and getting better designs. As it turns out, is also it makes it very easy to accommodate components made of different materials, and we've used it for that purpose to detect and quantify intersections between components, and we've also done that. And it makes it easier to impose certain geometric constraints. So for example, if you want to prevent certain kinds of overlaps, it's easier to do it when you have a separate density field for each one of the bars. So once we have defined the effective or the tensor of effective material properties using these interpolation rules, then we simply define our finite element analysis, for instance, the bilinear form in that way, right? When we compute the volume of the structure, we don't use penalization, meaning the power, the value of the exponent for the power law is 1. Otherwise, the penalization would not be effective. And one really nice thing about geometry projection is that the sensitivity analysis is relatively simple, because if you already have derivatives of your functions with respect to the densities, which we typically have them from density-based methods, then the derivatives with respect to the geometric parameters simply require a chain rule, right? So it's very straightforward. However, one thing to keep in mind, and this is going to be important for some of the things that I'm going to show in a few minutes, is that we have shown that to be able to have well-defined sensitivities always, it is necessary to have at least two elements through the smallest dimension of the geometric primitive. Not only that, but in general, to be able to correctly capture, for example, the bending of the primitive, it's good to have at least two elements, if not more, through the smallest dimension of the primitive. So if we put everything together, right, meaning if we look at how the optimization proceeds, what's the workflow for the optimization, it looks very similar to what we have for density-based methods, for example, with the exception of the geometry projection, right? So we do the geometry projection, we get the projected densities. With these densities, we compute the effective material properties, we do the finite element analysis and the adjoint analysis to compute the sensitivities. Then we evaluate those sensitivities, pass those to an optimization algorithm. If some stopping criteria are satisfied, then we stop. If not, then we continue, right? So it looks very much like density-based methods. The only thing that is added, if you will, is that now we have this geometry projection step. So let me show you a quick example. Here we have a simply supported beam. We're using symmetry boundary conditions. The load is applied here, and we're trying to minimize the structural compliance with a constraint on the volume fraction. And the initial design, which is arbitrarily chosen, looks like this. The level of the transparency of each one of the bars indicates the membership variable. So in this initial design, all the bars have a membership variable of 0.5. And what you see on the right-hand side is the projected or the combined density, really. And you see during the optimization that some of the bars are being entirely removed, right? Like this one, for example, it disappears, and this one, right? And that's really, the advantage of the membership variable. So with that, let me get to the application of geometry prediction techniques to large-scale problems. And let me preface this by saying that obviously density-based and level set methods have been very, very successful in solving a very wide range of problems in topology optimization. But the problems that I'm going to talk about here are problems for which trying to do the solution with field representations would be very, very expensive. And by taking advantage of some of the characteristics of geometry projection methods, we can solve these problems in a much easier way than what would be possible with, say, density-based and level set methods. So let me start with the design of slender and thin plate structures. One of the first applications that we made of plate structures, and this was actually motivated by my previous industry experience in the heavy machinery industry in Caterpillar, where we were trying to design these structures made of plates, right? So in this case, the primitives are plates, right? And so the initial design looks like this. The plates are just collapsed to a sphere. And as the optimization progresses, you see that we obtain a design that is made exclusively of these plates. And this is great, right? Because this looks a lot more like something that we can make out of, let's say, welded plates than what we would get out of the density-based topology optimization. However, this still has a limitation, right? And it is that because we need at least two elements through the thickness of the plate, right? Then there is a limit on how thin the plates can be relative to the design region, because if we have very thin plates relative to the design region, then the number of elements that we would require for the mesh, the final element mesh, would be huge, and it becomes impractical at some point. So the first solution that we put forward to try to address this problem was using adaptive mesh refinement. And just like the name says it, the idea is to refine the mesh to have it be essentially have smaller elements near the boundaries and coarser elements elsewhere, right? And the advantage of the geometry projection here is that the projected density or design distance provide a very easy way to have a refinement indicator. So wherever you have, you compute your geometry projection on a coarse mesh, right? And wherever you have elements that have intermediate values of the projected density, you mark those elements for refinement. Then you do the refinement, right? And you can repeat that for as many levels as you want. So you again repeat the geometry projection. You look at the elements that have intermediate values of the density. You mark those for refinement. You refine the mesh and so on, right? And so this is very, very convenient for two reasons. One is that unlike common methods to do adaptive mesh refinement, which are done based on some gradient of the solution, right? So they're significantly more involved. This is purely based on the geometry. So it's very easy, it's very quick to do, and it does not require a final element analysis, right? But the other very important thing is that because the geometry description or because the description of the structure is given by the parameters that describe the geometric primitives, right? When you refine the mesh, your design variables don't change. Whereas if you were to do something similar in density-based and level set methods, you have to deal with the fact that you're using the mesh to describe your structure, but then you refine it. So essentially you're also changing the description of your structure. And that introduces, of course, difficulties. So this is a small example in which we're trying to, again, design a simply supported cantilever beam. And it's shown here just so that you get a glimpse of how the adaptive mesh refinement is working, right? And so you see the optimization is essentially creating a coarse mesh in the void regions. And this is done at every iteration of the optimization, as you can see, right? So you repeat the adaptive mesh refinement at every iteration. And the advantage of doing adaptive mesh refinement is, first and foremost, that you need far fewer elements that you would need with a uniform size mesh that would have as the same number of elements through the thickness of the components, right? So in this example, actually, we require less than half the number of elements. And as you know, less than half the number of equations in finite element analysis can be significant for large problems, right? So for a more practical example, right, for the plates, we have this example where we're trying to design this structure made of thin plates, right? And again, the optimization is minimized compliance subject to a constraint on the volume fraction. If we were to use a uniform size mesh throughout the optimization for this problem, we would need a mesh that has 18 million elements, right? So that we can guarantee that we always have at least 2 elements through the thinner thickness of any of the plates, right? But with the adaptive mesh refinement, right, in the first iteration, we start with 6 million elements. It goes up to maybe 9 million or so. And then as the optimization starts converging, right, then we end up with a mesh of less than 4 million elements, right? And so the difference is drastic, of course. And so we can solve this particular problem in 8 hours. Actually, this was quite a few years ago already. So the specs of this machine and the times were for the specifications of that time. But the point is that we can design this structure that now can start having much thinner plates, and you can see that in some of the plates here relative to the size of the design region, right? We also use the same approach to design sandwich structures where the reinforcing ribs in the panel are made of a composite laminate. And in this case, the objective function is a weighted compliance, and we have a volume fraction constraint. And what you see at the top is the designs that we obtain when the structure is made of aluminum, and then at the bottom when it's made of a carbon fiber reinforced polymer. And here we have the designs for a volume fraction of 5% and a volume fraction of 10%, which are even, already relatively low volume fractions compared to what we typically do with field representations. And here you can see the adaptive mesh refinement for this problem. There is another strategy that we can use to go about this problem of the structure having a very low volume fraction relative to the design region. And so we use that in what we call design of ultralight frames made of structural profiles. And the goal here, the animations are not correct here, but what we want to design is what we call ultralight frames. This is maybe a misnomer because a lot of practical truss-like structures are already ultralight. But our definition of ultralight is that the volume fraction relative to the volume of the design region is less than 1%. Typically, no matter what the problem that you're trying to solve, if you want to get to a volume fraction of less than 1% with density-based and level set methods, that's tough. You would need a very, very, very fine mesh. It can be done, right? But essentially, you need a really fine mesh so that you can get a very small details. And so that's already, a challenge, meaning the fact that we have a relatively low volume fraction relative to the design region. But on top of that, if we want to use these sort of structural profiles, now we have to take into account that these structural profiles themselves have these, kind of relatively small features relative to the dimensions of the profile itself. And so that makes it even more difficult. And, using ground structure methods for these problems is possible, but ground structure methods have their own challenges in terms of producing suboptimal minima. And also removing members from the design is actually quite challenging sometimes in ground structure methods. And so the solution that we came up with was to use what we're calling an equivalent section approach. And you can think of this as and maybe when I'm saying this is maybe a little bit heretic, but essentially what we're doing is ultimately a homogenization of sorts, right? A homogenization of the geometry. And what we're saying is we're going to replace the true cross-section, right, of the structural profile with another rectangular cross-section of larger dimensions that has the same effective stiffness, axial stiffness and bending stiffness. And we do that simply by equating the axial stiffness of the two sections and then the bending stiffness in the weak and the strong axis, right? And so you can have any sort of profile here, right? Your rectangular section would have an equivalent Young modulus, right? An equivalent cross-sectional area and equivalent area moments of inertia in the strong and weak axis, right? And so the advantage here is that instead of having to have two elements across this tiny web, for instance, in this I-beam, right? I can have this much larger rectangular cross-section, right? That is going to require, far fewer equations in the finite element analysis, right? And note that it's not just the dimensions, we're also having a different modulus for this cross-section, right? So intuitively is sort of a straightforward approach, and this is an example where we're trying to design a bridge, and we really use symmetry boundary conditions, and so we do the optimization, I believe, only for a quarter of the bridge. And so here you can see how the optimization is progressing. And when we do the optimization, we compute the limit on the volume fraction using the equivalent section. But the true volume fraction of this structure, if you go back to the dimensions of the original profiles, is 0.2%, right? And again, this would be very tough to do with density-based and level set methods, right? And this is just an example of that bridge design with kind of a design that looks similar in ANSYS, and the difference in the compliance is of about 11%. So obviously there is some modeling error in using this kind of geometric homogenization approach, but I think it does nevertheless very well in terms of producing these designs. Another instance in which a geometry projection can help solve problems that are very expensive to solve density and level set methods is in fail-safe design. So fail-safe design is the kind of design where we seek safe operation of the structure if a portion of the structure is lost. For example, if there is some impact and you lose a part of the structure. And in topology optimization, in the literature, this usually has been posed as a min-max problem, where, for example, in the case of compliance, if you have, if you lose different portions of the structure and compute the compliance for the structure for each one of those cases where you've lost a portion of the structure, then you want to make sure that the largest compliance that you get of any of those cases where you've lost a chunk of the structure is as small as possible, right? So it's a min-max problem, right? Now, density-based methods have addressed this problem in essentially the same way, which is that they remove a patch of elements, right? So they make the densities of this patch of elements 0. They solve the analysis, they compute the compliance, then they move this patch a little, right? And so in this paper, the patch is aligned with the element edges, so you would just move the patch by one element column. And you do the same. You make the densities in that patch 0, you run the analysis, and so on. And so for each iteration of the optimization, you have to solve as many finite element analyses as possible positions of this patch. And this other method is just a variation of the same method, except that instead of moving element by element the patch, you have a tiling of all the patches. So it still requires it requires a far fewer finite element analysis, but it nevertheless, requires still a lot of finite element analysis. Well, in geometry projection, the idea is that if you lose a member, you just remove that member from the mesh. And so you just have to essentially turn off that structural member from the design. And so the number of finite element analysis that you have to do in each iteration is just the number of geometric components that you have in the mesh, regardless of the element size in the finite element mesh, right? And so we use this unmasking approach where for each one of the primitives, we make sure that the densities in the region occupied by that primitive are 0, and then we run the analysis, right? And by doing that, for instance, we're able to produce fail-safe designs for three-dimensional problems, which is very, very expensive to do with existing methods for density-based and level set techniques. Another case in which using geometric primitives can be advantageous in terms of large-scale problems is in the use of off-the-shelf solvers. And so there are some situations in which using off-the-shelf solvers can be advantageous, right? An off-the-shelf solver has typically a lot of formulation, particularly if it's like a commercial tool or maybe software that is, let's say, created at one of the national labs or what have you. You have different formulations. You can handle very complex geometries. You can handle problems where the mesh is made of many different types of elements, right? Maybe you have spider elements. Maybe you have a portion of the mesh that has two-dimensional elements and another portion has solid elements, what have you, right? This is a lot easier to handle in off-the-shelf tools than it is in, let's say, research codes, right? And so in geometry prediction methods, the fact that we have far fewer design variables, namely the geometric parameters that describe the primitives, right, means that even though it's expensive, it's still nevertheless possible to compute the design sensitivities using finite differences, right? And so you can just use your off-the-shelf solver, right? Do this in parallel, let's say in a high-performance computing system, and get your finite difference sensitivities and run the optimization doing that. And so here are two examples of how we've used that. One is in the topology optimization of plate heat exchangers. And so here we have a plate heat exchanger. We have a hot fluid coming through this port and leaving through this port on the other side, a cold fluid coming through this port and leaving through this other port on the other side. And so the hot fluid goes in between some of the plates and the cold fluid goes in the other plates, right? So that essentially you have heat transfer from the hot fluid to the plate to the cold fluid on the other side. And the goal here is to design these flow structures in the cavities inside each plate to try to maximize the heat transfer, which here we compute as the difference in the enthalpies between the outlet ports for the hot and the cold fluids. And then we have a constraint that the pressure drop cannot exceed a prescribed value, right? And so this is how the optimization works for this particular problem, right? We assume symmetry along the diagonal, and also to reduce the number of design variables for which we have to compute sensitivities, we assume the design is the same on both sides, on the cold side and the hot side, but the one on the other side is essentially rotated 90 degrees. And so in this case, our off-the-shelf solver is AccuSolve, which is the CFD solver in the Altair Siemens suite. And one advantage of this particular method is that the design that we get can be fabricated using additive manufacturing techniques very easily and exactly as it's coming out of the optimization. The other example where we have used an off-the-shelf code is for the topology optimization of sandwich panels for energy absorption, right? And here the off-the-shelf code is LSDyna. We have a unit cell, and so the design variables describe the layout of these bars in this unit cell. And then in the analysis, we just repeat this unit cell several times, right? So there's no periodic boundary conditions. We're actually making copies of the unit cell many times, but the design variables describe only one of the unit cells. And then the other thing that we do is that we remove elements at each iteration as the design is changing. We remove elements in the void region to make it possible to actually use general contact and capture contact in between these struts, and to make sure that the structure is always connected to the face sheets of the sandwich panel. We make sure that we don't remove elements sort of in the extension of these struts. And so here is an example in which we're trying to simultaneously maximize the plastic work and minimize the displacement at the bottom face sheet of the panel, right? And this is the initial design, and this is the unit cell that we're designing. And as I said, we just repeated many times, right? And so the optimization is modifying the design parameters. At each iteration is calling LSDyna as many times as design variables as we have to compute the finite differences, passes those to the optimizer, and then it repeats the process to do the optimization. And we see that the optimization is increasing the plastic work and decreasing the displacement at the bottom panel. Okay, finally, the other example where geometry projection techniques is advantageous in terms of problems that would be too expensive to solve with field representations is in the reliability-based topology optimization with dimensional and positional variability. And here we want to design assemblies of structural profiles, again, where now we would consider the variability in the dimensions of the cross-section of the individual members of the structure. And also we would like to consider variability in the positions of those members within the structure that may arise, for example, from the assembly process, right? So for instance, from process-induced dimensional variations caused by, for instance, welding, right? And we're interested in particular in being able to solve what we call the reliability-based topology optimization problem, in which we're minimizing, for instance, the weight of the structure subject to a constraint that the probability that some structural measure of the structure exceeds some value is let me be clear about this. The probability that a failure function is less than some prescribed value, right? Or that the probability of some structural success function is greater than some prescribed probability value, right? And so here we're essentially thinking about the variability, statistical variability in the dimensions of these components and the position, as I mentioned. And the advantage provided here by geometry projection techniques is that we have far fewer design parameters than that we do in field representations. And that makes it possible to use surrogate models to have an accurate prediction of the reliability of the structure. And this is really the sort of the part where geometry projection becomes advantageous in the context of this problem. Also, one advantage of this approach is that the variability in the dimensions of the members, right, is something that relates to actually measurable quantities, right? I mean, you can get a batch of these structural members and then try to essentially have a quantification of the distribution of the dimensions of those stock material, right? Which is something that is not as easy to do with density-based and level set representations. So what we do here is a staggered approach where we decouple the deterministic topology optimization from the reliability analysis, and we build an accurate surrogate of the design coming out of the deterministic topology optimization. We use it to evaluate the reliability, and we use that to modify the constraint limit in the next deterministic topology optimization run. So we run a deterministic topology optimization with the limit on the performance function that we want. So this is just a plain vanilla regular topology optimization. At the end of this topology optimization, then we build a surrogate of the failure function G, right, around the design. So it's just a localized surrogate, right, around the design coming out of the deterministic topology optimization. And once we have that surrogate, that's very quick to evaluate. So we can just use Monte Carlo sampling to figure out what is the quantile corresponding to the reliability that we're seeking. And we use that essentially to go back and modify the limit on the constraint, right? And so we do this in an iterative way until some stopping criteria are met. And so here are some examples. This is a compliant mechanism design in 2D. The initial design looks like this. And this is the design that we would obtain using just deterministic topology optimization. And it has a very small probability of success, right? 8.4%. And these are the designs that we are obtaining with the proposed method, right? For different values of the target reliability, right? So this is 84% reliability, 93%, and 97 or 98%, right? And so clearly you see different designs, right? And notably, we're getting different designs than the ones that we get with the deterministic topology optimization, but also that we get with other methods, such as those based on the first order reliability model approximation. And so they're not only different, but they're actually quite more reliable than the ones that we would obtain with form. And then, the sort of the demonstration that this is computationally feasible is that now we're doing it with three-dimensional problems, right? So this is just a 3D cantilever, and in this case, the reliability function or the failure function would be compliance. So I'd like to, and I rushed a little bit the last few slides. I'm sorry about that, but I just wanted to leave time for questions. These are the references to our work, and I understand that the recording and/or the presentation will be distributed afterwards. But with that, I would like to thank you again for your time today, and I'm happy to take any questions that you may have.
So thank you very much, Julian. Really appreciate. I enjoyed your talk. So now floor is open to the question, and I see that we have a good number of the people, including some of the prominent people from topology optimization. So any question? Okay, I will start before. So first of all, we have some question in the chat. I forgot about that. Let's start from those questions, and then I can go. So the first question is from Ali, is asking, which software have you used to create the 2D optimizations?
That's code that's our own research code. So we write that. The only exception, for the problems where we use the off-the-shelf solver, the solver itself is a commercial code, but everything else is also our code. Yeah.
Okay. So please actually unmute yourself and ask question, or put it in the chat, and I will read for Julian. But I will start with the first question from mine. So it is a very general question, Julian. Here you are using different members actually in the plate or the bars. Are you considering how they are jointing to each other? Because in the topology density-based topology optimization, usually we have a continuous domain, yes?
Yes.
And here it is different member, they are jointing to each other. Are you considering even some joint consideration in your design?
So let me answer that in two parts. The first is that in terms of the finite element analysis itself, the assumption that we're using so far, right, is that when we do this combination of properties using this maximum function, this is equivalent to a Boolean union.
Yes.
So this is equivalent to assuming that whenever these primitives intersect, you're just doing a Boolean union. So this is, for all practical purposes, is just a monolithic part, right? Now, in practice, that may not be the case. And I believe this is perhaps where your question is coming from,
yes.
Right? And so the answer is we have started looking at that. We published something perhaps a couple of years ago where we do topology optimization to minimize manufacturing costs of welded frames, in which the objective function is manufacturing cost, and one of the terms in the objective cost function is the weld length. So the fact that we have this different representation of primitives, different density representation of the primitives, allows us to actually approximate the weld length between two of those. So that's a consideration of the joints in terms of cost. Structurally, we also have done some preliminary work to do stress-based topology optimization, where we have different strength constraints for the joints than we do for the rest of the structure, right?
Yes.
And that's also possible here, because when you have the different representation for the different primitives, you know where the joints are, right? Which it's more difficult to figure out, let's say, in density-based or level set methods. I don't know if that answers your
No, yes,
uh-huh. Yeah.
you answered. Thank you very much. So there is a question from Lawrence. It says, in the modified p-norm combination of the primitive, how does the choice of the parameter p affect the smoothness of the material distribution and the tendency of overlapping primitives to behave like a union versus a blended material region?
So these approximations of the maximum function are always tricky. I think they solve a problem and they give us other problems, right? And so you cannot use a value of p that is too high, because then the optimization functions will become too nonlinear in the design variables, and that makes it very difficult for the optimizer to do its job. But you cannot use a value that is too low, because then it's really not going to do a good job of approximating the maximum. And so this requires some level of tuning, right? And we have to play with those values. And we typically try to choose values of p, right? Such that wherever they intersect, you do get essentially a density of one in the intersections, right? So if you get any sort of variabilities more towards the boundaries, right? But I would say that an important thing is that the sharpness of the boundaries, right, in the primitive is not connected to this p-value, because it's given by the radius of the sampling window that we use to compute the geometry projection. So no matter what value of p you use in this combination, right, the width of the boundaries is always the same. And I don't know if this is really answering the question, but I hope at least partially it does.
And Lawrence, if you wanted to follow up, please unmute yourself. Otherwise, I will go to the next question. Okay, so Ali asking, it is regarding the orientation of these members. He is asking, in lattice structure, orientation plays a crucial role because the majority of the struts should ideally be loaded in tension or compression. How would you determine or optimize the lattice orientation for this purpose, to have under tension or compression?
If we're doing the minimization with respect to compliance, we don't have to do anything.
It is natural.
Because the compliance problem, if you want a structure that is as stiff as possible, right? What the optimizer is going to want is, as much as it can, to have members that are only acting in tension or compression. So we don't have to do ourselves anything about it. There's obviously limitations, right? So if your volume fraction is so low that you can really not have a connected structure where some of the members are in bending, then you're going to get some bending, right? But that would be how your optimization problem is defined anyways. So, but yeah, we don't have to do anything in particular. In 2D, it's even easier, because in 2D, we know that the stiffest designs are made of straight bars, right? In 3D, the stiffest designs are made of thin plates, but if we use bars, nevertheless, the optimizer tries to get something that is in tension as much as possible, right? That depends, however, very much on what your objective function is, right? So when you're designing lattices, and we have done that, and I didn't show here because it's not one of what we would call the large scale problems, but in the design of lattice structures, if you're looking, for example, to, let's say, minimize the effective Poisson's ratio, right? Then that's going to be the opposite, right? You're going to have a structure actually that bends quite a bit, right?
Okay, thank you. Any other question from the audience? Okay, in the last 4 minutes that I have, I wanted to ask one more question regarding your experience. It is not a research, but it is your experience in industry, in academia, specifically for our younger student and postdocs in the audience. So could you explain a little about your experience after getting your PhD? You went to industry, working there, and then in academia. What is your feeling in both? Please give your honest answer for our audience. So because we received this question, they wanted to decide which direction go.
Well, that's a very personal decision, because it depends on a lot of things, right? And I would say that even if you go to industry, your experience in industry can vary widely depending on what is the job that you end up getting, right? I was very, very fortunate to end up in a group where I could do research. As a matter of fact, I think the thing that I enjoyed the most about the group that I work with was the fact that we could work with the business units to try to solve their problems. And that was sort of what motivated some of the research and development, right? And so it gave me the possibility of having those three aspects, right? The development of tools, the solution of practical problems, and the research. But that was very unique. And I was, as I said, very, very lucky in that sense, right? If you end up working in a different kind of job in industry, where maybe as a PhD graduate, you have to, or a master's degree graduate, you have to work on tough problems, but it's still like individual problems. Let's say that some system is failing in some way and you have to figure out why, right? It can be a different experience, right? And I'm not saying it's better or worse. It depends on what you like, right?
Yes.
And so I think that's very variable. I think I was very, very fortunate to have been able to do the things that I did in industry. They are connected to what I'm doing here in academia. So I guess in that sense, it's been sheer luck to a good extent.
Okay, so thank you very much. Any other short question from audience? If no, let's thanks one more time, Julian, for this
Thank you so much.
beautiful presentation and good talk.